All right, so today we're going to be looking at evaluating time complexity of the algorithms and the functions that we theorize and write out. So, motivation for analyzing time complexity is pretty simple. We want to know how long it'll take our programs to run. This is sort of a very surface level explanation. A more specific one is that we want to be able to define an upper bound of the worst case runtime of an algorithm relative to the size of its input that we will denote with a character n. And this is a very this last part uh, is an incredibly important distinction that we'll get into later. Um, and we are looking for specifically an upper bound of the worst case runtime because if we can accommodate through uh, hardware, if we can accommodate the worst case runtime of an algorithm by accommodating the upper bound that we find, um, we will be accommodating every other case in which the given method or function or algorithm will run in. A couple of examples of time complexity problems very quickly. These are things that you would run into in introductory data structure classes. Um, when you're trying to sort or search a data structure, the complexity of say that the search uh, method is going to differ with the structure that you use relative to its size. So things like a linked list, a tree, an array, as those data structures get bigger, as you add more elements, the time it takes to search through them is going to change by differing rates and amounts. Another great example is searching through a frontier graph, which is a graph made up of states that are connected by actions. Very, very important abstraction for uh, the field of artificial intelligence. If we know the size of such a graph and we're searching for a certain end node or a goal node, we can analyze the complexity of that search itself. And then there are things like solving puzzles like Sudoku, where in upper level classes you'll learn about how problems like Sudoku are actually have a uh, not quite defined but very strongly theorized upper bound to how quickly you can solve them relative to their size. So we'll go over notation very quickly here. Complexity is denoted by some expression where the only unknowns are the inputs to the algorithm being analyzed. So pretty much what this means is that for the example that we have here, given an input f of n, where n is denoting the size of whatever argument we input to f, we would denote its runtime with something like uh, big O of n, where this is what we would say if the function f ran in something called linear time, which we'll explain later. But this could be the expression within the brackets succeeding the big O could be any expression relative to uh, the value n. So it could be n squared, n cubed, 2 to the n, log n, so on and so forth. So something that you might have picked up on already is that analyzing for complexity is entirely relative to the input size, which I want to give a specific example of what that means here before we dive into some problems. So we have these two functions here. Both of them have loops, and within either of these loops, they're doing the same exact thing. That it's completely arbitrary what they do, but you know that whatever they do, it doesn't matter how big n is. N could be 1, n could be a billion, and whatever happens within these loops for every iteration, um, it's not going to take any extra time. So with that being known, which one of these is going to run faster? Well, obviously, we can see that if they're doing the same exact thing for each iteration, and regardless of what the input size of n is, the loop on the bottom right is going to run 1,000 times more iterations than the loop on the top left. So because of that, we can say that most likely the loop on the top left is going to run around 1,000th of the time that the loop on the bottom right does. However, this is not really what we're analyzing with complexity, because this measurement is not relative to the input size. It's relative to the it's really relative to each other, but that's I digress. If we want to analyze complexity, a better thing to do is look at what happens when we put in a certain input, see how long each of these will run, and then by how much will the runtime change if we change the input. So, for example, if we input n to both of, or if we input 1 to both of these functions, where n equals 1, the top function will run through its loop once, and the bottom function will run through its loop 1,000 times. Now, if we double the input size to 2, how many times are these loops going to run each? Well, for 1, our top left loop here ran once, and for n equals 2, it's going to run twice, because that's just how the function is defined, or the loop is defined. And if we double the input size to 2 for the function on the bottom right, we'll see that the number of times that the loop runs goes from 1,000 to 2,000. So although these functions differ in their runtime, they are the same in the factor at which the runtime increases as the input size increases. So you can see that as n doubles for both of these functions, their runtime roughly doubles as well, as the number of times that the top left loop runs goes from 1 to 2, and the bottom right loop goes from 1,000 to 2,000. So if the input size doubles, their runtime roughly doubles. And because of that, because they directly scale with the number of times, since they directly scale, their runtime directly scales with the input size, we would say that both of these functions run in linear time. Now we'll go into some examples where we have functions that will not run in linear time, and how can we look at these? Well, if we look at this function, we'll see that we have an outer loop that is equivalent to the loop that we had in our first example, and the inner loop is also going to run the same number of times. So both of these loops run n times, but since it's a nested loop, this inner loop is going to run n times for every one iteration that the outer loop runs. So when we're analyzing complexity, when we're trying to determine the approximate runtime, we're going to be asking how many times does whatever is inside this inner loop runs. How many times does this block of code run? And what we're going to do to analyze this is we're going to look at a table like this, where we can plot input size, or we can plot runtime relative to the input size, and we can also look at the change in runtime as we increment the input size. So if we look at these, if we fill out these cells, we see that the runtime is going to be exactly the input size squared. And we specify runtime relative to n equals 1 because that's the again, since we're analyzing for relative to the input size, that's that's where that comes in. So we can see that instead of scaling directly with the input size like we had on the last one, where, when we doubled the input size value from 1 to 2, instead of the runtime doubling, it's going to be quadrupling. So as we can see, these first two columns actually just plot the function n squared. And so that means that the runtime increases at a faster rate than the input size increases, and it increases progressively at a faster and faster rate, which we can see in the third column here, as the change in runtime is progressively increasing as well. So because of this, we can say that the complexity of this function is big O of n squared, because our runtime is no longer scaling directly with our input size. Now we have another nested loop as an example here. It's a little bit different, and the changes here are worthy of noting. So from our previous function, we have a nested loop, and the inner loop runs n times and the outer loop runs n times. But for this new function, our outer loop runs n times again. However, our inner loop runs only 3 times. Now, something we're going to see from this is, or something that's important to note, is that this inner loop, every time this inner loop runs, it doesn't matter how big n is, it's going to run 3 times. And whatever is inside of it, again, it doesn't matter how big n is, whatever is inside this inner loop is also going to run in the same amount of time. So because of this, we can say that this inner loop entirely runs in constant time, which means, or we can also denote this as big O of 1 time. And essentially all this means is that as n increases or decreases, the amount of time that it'll take this inner loop to run will not change whatsoever. So because we know that, we can then evaluate the outer loop. We can see that it'll run n times, and then whatever is inside of it will run exactly 3 times. So our input size is going to, so to get the function that maps our input size to our runtime relative to n equals 1 is going to be 3 times n. And that makes sense because, again, this inner loop runs 3 times regardless of how big n is. So although this runs more times than, say, the linear runtime function that we started out with back here, where we have one loop that runs n times and then it does something. We have whatever is inside this inner loop, it runs 3 times for every n. However, that doesn't matter when it comes to analyzing complexity, because again, we're just talking about the rate at which the runtime scales as we increase n. So if we look at this third column, we'll see that the change in runtime is constant for every single increment of the input size. So because of that, although we are increasing the runtime more than 1 for every time we increase n by 1, it's still increasing at a constant rate. So because of this, this function will still run in big O of n time, which makes sense with what I was saying before, because since this inner function runs in constant time relative to n, if we run something in constant time n times, then that will be a linear time operation. All right, so now we're going to switch it up a bit. We're going to look at a different type of function. Instead of analyzing just a loop with an explicit upper bound that is some multiple of n, we're going to look at something a little less straightforward. We're going to look at a simple recursive function. Now, analyzing complexity for recursive functions, well, first we need to analyze the runtime of a recursive function, and there are more complex ways to do it, but the simplest way for now, or the only way that we're going to really need to pay attention to here is how many times is f called for an input size n. So with this function, we can see that all we're doing is recursively calling this function once for every time, once, and then we input the decremented original input. So from this, we can see that the function will simply run n times, because for every time we decrement n, it's going to be 1 closer to 0, and we've recursively called f once by doing that. So if we fill out the table here, it's going to be pretty straightforward. As the input size increases by 1, or as we increment the input size, we're going to be incrementing the number of recursive calls to f itself. So the change in runtime is going to be at a constant 1 for every time we increment the input size. So just like the first method that we looked at, this is going to be running in linear time. Now, the final example that we'll go over is another recursive function. This is not run in linear time, but let's take a look. So just like our last function, we have this base case where when n equals 0, we return. And if it's greater than 0, we're going to return, or we're going to recursively call f twice with an input of decremented n for both. So when we think about this, again, for analyzing runtime, we're going to be looking at how many times is the function called in total. Now, if we had an input of 1, we would skip the base case because 1 doesn't equal 0, and then we would recursively call f twice with an input size of 0. So that means that for an input size of 1, we call f twice, which means we're going to have a runtime, or an approximate runtime of 2. And then what happens when we increment this? Well, if we call f of 2, again, we'll skip the base condition, and then we're going to return 2 recursive calls to f, where the input is going to, for both of them, be 1. But we already determined the runtime of f of 1. We know that it's 2. And we're calling f of 1 twice in this return statement. So that means that we're going to be doubling the runtime of f of 1 to equal the runtime of f of 2. So the runtime of f of 2 is going to be 4. And that rule is going to persist as we increment the input size, that for every time that we increment the input size, the runtime is going to double. Now, this is a greater rate of change than anything that we've seen so far. This is a greater complexity than anything we've seen so far. Because even with big O of n squared, your rate of change is increasing over time. Your rate of change of the runtime is increasing as you increment n, but it's still only increasing additively, where in this example, our change in runtime is increasing multiplicatively. In fact, the change in runtime is just the runtime itself shifted one row down. And you might recognize this relation as an exponential function, where for every time that we linearly increase the input size, we're going to be multiplicatively increasing the runtime. So because of this, we're going to denote this as big O of 2 to the power of n. So this runs in exponential time, and this is a very bad case for runtime. And in higher level material, you'll understand, or you'll learn how to mitigate the use of exponential complexity algorithms, because when you have something running in exponential time, as you scale up the problem, it gets out of hand for pretty much anything very quickly. All right, so I think that wraps it up for today. I hope you've enjoyed.